Imagine you are standing at the bottom of a gentle grassy hill. In your hand you hold a red rubber ball. Your goal is simple. Get the ball to the other side of the hill. You give it a gentle push, and it starts rolling up the slope. But alas, you didn't give it enough energy. The ball slows down, stops, and then rolls right back down to your feet. You try again, pushing a little harder, but the result is the same. In our everyday world, the rules are clear and dependable. To get over that hill, the ball needs a certain amount of energy. Without it, the hill is an impassable barrier. It's a law of physics you can count on, as reliable as gravity itself. Now, let's think about that same scenario with one tiny change. Instead of a big rubber ball, imagine you have a particle so small you can't even see it. An electron, for instance. This is where the world starts to get wonderfully weird. You give this electron a push, sending it toward the same hill, which now seems like a colossal mountain to our tiny particle. Just like the ball, the electron doesn't have enough energy to climb to the peak. According to the rules we know and trust, it should roll right back. But then, something impossible happens. The electron vanishes from your side of the hill, and in the blink of an eye, reappears on the other side. It didn't go over the top, it went through it. This mind-bending feat is the essence of one of the most fascinating ideas in all of science: quantum tunneling. It breaks every rule we learn from throwing balls, driving cars, or climbing stairs. In the familiar, large-scale world governed by classical physics, barriers are absolute. If you don't have the key, the door stays locked. If you don't have the strength, the wall is insurmountable. This is the world of common sense, the world we navigate every single day. The rules are straightforward, and outcomes are predictable, giving us a sense of order and reliability in how the universe works around us. But at the quantum level, the realm of atoms and particles, the universe plays by a completely different set of rules. Here, possibilities replace certainties. Particles aren't just little specks. They also behave like waves, spreading out in space like ripples on a pond. Because of this wave-like nature, a particle doesn't exist in just one single spot. Instead, there's a cloud of probability, a region where it could be. And sometimes a little piece of that probability cloud can leak through a barrier that should have been impenetrable, allowing the particle to perform its vanishing act and appear on the other side. This is the magic of the quantum world, a place where the impossible becomes merely improbable. So, how can a particle pass through a solid barrier? The answer lies in one of the central ideas of quantum mechanics' wave-particle duality. This concept tells us that the tiniest objects in our universe, like electrons and protons, don't just behave like hard little balls. They also act like waves, spread out through space. Think of a beam of light, which is made of particles called photons. We know light acts like a wave. It can be bent, reflected, and create interference patterns. But it also acts like a stream of particles that can knock electrons off a metal plate. This dual nature is shared by all matter, though it only becomes noticeable for things that are incredibly small. When we think of a particle as a wave, its location isn't a single precise point anymore. Instead, it's described by something called a wave function. This wave function is like a mathematical cloud of possibilities. Where the wave is high, there's a high probability of finding the particle. Where the wave is low, the probability is small. Now imagine this wave approaching a barrier, a wall of energy it doesn't have enough oomph to climb over. In the classical world, the story would end there. But in the quantum world, the wave function doesn't just hit the wall and stop. A part of it actually penetrates into the wall. Inside the barrier, the wave function changes. It starts to decay, getting weaker and weaker the deeper it goes. For a very thick or high barrier, the wave will fade away to almost nothing. But if the barrier is thin enough, the wave function doesn't completely disappear. A tiny, faint whisper of the wave can make it all the way to the other side. This faint whisper means there is a small, but not zero, chance of finding the particle on the far side of the barrier. If we were to check, we might find the particle has tunneled through, even though it never had the energy to go over. It's a bit like hearing a muffled sound through a thick wall. The sound wave travels through the wall, even though you can't. The probability of this happening is incredibly sensitive to a few key factors. The thicker the barrier, the less likely tunneling becomes. The higher the energy of the barrier, the less likely it is too. And finally, the more massive the particle, the smaller the chance of it tunneling. This is why we never see a tennis ball tunnel through a wall. It's just too big and heavy. The wave associated with it is so incredibly tiny that its chance of tunneling through anything is practically zero. But for a lightweight electron facing a barrier just a few atoms thick, tunneling isn't just possible. It's a regular and predictable event that shapes the world at its most fundamental level. The idea of quantum tunneling didn't just appear overnight. It was the result of brilliant minds wrestling with the strange new rules of the quantum world in the early 20th century. The story begins in the 1920s, a revolutionary time in physics when scientists were developing the very language of quantum mechanics. In 1927, a German physicist named Friedrich Hund was one of the first to notice this peculiar effect while applying the newly minted Schrödinger equation to understand how molecules are structured. He realized that the equation predicted that a particle could, in theory, exist in a place that should have been forbidden by the laws of energy. Just 1 year later, in 1928, this theoretical curiosity found its first major real-world application. The physicist George Gamow and independently Ronald Gurney and Edward Condon were trying to solve a puzzle about radioactive decay. Specifically, they wanted to understand how an alpha particle made of 2 protons and 2 neutrons could escape from the powerful forces holding it inside an atomic nucleus. The energy barrier holding the particle in was immense, far greater than the energy the particle itself possessed. Classically, it should have been trapped forever. They realized that tunneling was the key. The alpha particle was behaving like a quantum wave and tunneling its way out of the nucleus. For the next few decades, tunneling remained a somewhat exotic concept, but that all changed in the second half of the century as scientists began to explore the quantum behavior of materials. In 1957, the Japanese physicist Leo Esaki was studying semiconductors when he discovered that electrons could tunnel across a very thin junction between 2 different types of materials, creating a device now known as the tunnel diode. A few years later, in 1960, Norwegian-American physicist Ivar Giæver demonstrated tunneling between superconductors. Then, in 1962, British physicist Brian Josephson predicted that pairs of electrons could tunnel through an insulating layer separating 2 superconductors, a phenomenon now called the Josephson effect. These discoveries were so fundamental that Esaki, Giæver, and Josephson shared the 1973 Nobel Prize in Physics. The final triumph in the story of tunneling's discovery came in 1981. 2 scientists at IBM's research lab in Zurich, Gerd Binnig and Heinrich Röhre, had a revolutionary idea. They wondered if they could use quantum tunneling to see individual atoms. They built a device with an incredibly sharp metal tip, which they brought almost infinitesimally close to a surface. By applying a voltage, they could make electrons tunnel from the tip to the surface. Since the tunneling rate is so sensitive to distance, they could create a stunningly precise map of the surface, atom by atom. This invention, the scanning tunneling microscope, opened up the field of nanotechnology and earned Binnig and Röhre the 1986 Nobel Prize in Physics. Quantum tunneling isn't just a quirky phenomenon found in a lab. It is a fundamental process that powers the universe itself. Perhaps its most magnificent role is inside the core of our sun and every other star in the sky. Stars shine because of nuclear fusion, a process where the nuclei of light atoms like hydrogen are squeezed together to form heavier atoms like helium. This process releases a tremendous amount of energy in the form of light and heat. However, there's a big problem. Every hydrogen nucleus, which is just a single proton, has a positive electrical charge. And as you may know, like charges repel each other with a powerful force. For 2 protons to get close enough to fuse, they have to overcome this intense electrical repulsion known as the Coulomb barrier. The core of the sun is incredibly hot, about 15 million degrees Celsius, and the pressure is immense. This gives the protons a lot of energy, making them zip around at high speeds. But even at these extreme temperatures, the protons don't have enough energy on average to smash through the Coulomb barrier head-on. According to classical physics, the The sun shouldn't be hot enough to ignite nuclear fusion. The stars simply shouldn't shine, and yet they do. Our existence is a testament to the fact that something else is at play. That something else is quantum tunneling. Even though a proton doesn't have enough energy to climb over the top of the repulsive energy barrier, its wave-like nature gives it a small chance to tunnel right through it. Each time two protons approach each other in the sun's core, there's a tiny but non-zero probability that they will tunnel close enough for the strong nuclear force, a much more powerful but shorter range force, to take over and bind them together. This initiates the first step of the fusion chain that ultimately powers the sun. Without tunneling, this crucial step would almost never happen. This process is a delicate balance. The probability of any single proton pair tunneling is extremely low, but the sun's core is so dense with protons that these improbable events happen countless times every second. This steady, sustained rate of fusion is what has allowed our sun to burn consistently for billions of years, providing the stable energy source needed for life to evolve on Earth. So, the next time you feel the warmth of the sun on your face, remember that you are experiencing the direct result of quantum tunneling. The light that traveled 93 million miles to reach you was born from a quantum leap through an impossible barrier, deep within the heart of a star. The influence of quantum tunneling extends beyond the fiery cores of stars and into the intricate, delicate machinery of life itself. It plays a subtle but potentially profound role in the very code of life, our DNA. The DNA molecule is a famous double helix, two long strands connected by rungs made of pairs of molecules called bases. These bases are held together by weak connections called hydrogen bonds. In these bonds, a single hydrogen atom, a proton, is shared between the two bases. Normally, this proton sits closer to one base than the other, creating a stable and correct pairing: adenine with thymine and guanine with cytosine. This precise pairing is what ensures our genetic code is copied accurately. However, the proton is a quantum particle. It is not fixed in one spot, but exists as a probability wave. This means there is a small chance that the proton can spontaneously tunnel through the energy barrier within the hydrogen bond to a new position, closer to the other base. When this happens, it creates a rare and unstable form of the base, known as a tautomer. This is a tiny, fleeting change, and most of the time the proton tunnels right back to its original stable position without causing any harm. The system corrects itself, and the integrity of the genetic code is maintained without any issue. The trouble begins if this quantum tunneling event happens at the exact wrong moment. Specifically, during the instant when the DNA double helix is unzipping to be replicated. If a proton tunnels just as the replication machinery arrives, the altered base can cause a mismatch. For example, a tunneled adenine might now incorrectly pair with guanine instead of its usual partner, thymine. This introduces a tiny error, a mutation, into the new DNA strand. This is called a tautomeric transition, and it's a form of spontaneous mutation driven by a purely quantum effect. It's like a ghostly glitch in the biological machine. Scientists are still exploring the full implications of this phenomenon. Some theories suggest that this kind of proton tunneling could be a contributing factor to the natural rate of spontaneous mutations observed in all living things, which drives evolution over long timescales. Other, more speculative ideas link the accumulation of these quantum-driven mutations over a lifetime to the processes of aging and even the development of certain cancers. While the direct impact is difficult to measure, it's a powerful reminder that the strange rules of the quantum world are not confined to physics labs. They are operating deep within our own cells, potentially shaping our biology in ways we are only just beginning to understand. While quantum tunneling can feel abstract and distant, it is the engine behind some of the most transformative technologies we use every day. One of the most direct and amazing applications is the Scanning Tunneling Microscope, or STM. Before the STM, our ability to see the world was limited by the wavelength of light. We could never see an individual atom because atoms are smaller than a single wavelength of visible light. The STM shattered this limitation by not using light at all. Instead, it uses a quantum phenomenon, the flow of tunneling electrons, to feel the atomic landscape, much like a blind person reads Braille. The STM works by positioning an incredibly sharp metal tip, sometimes tapering down to a single atom, just a nanometer or two above the surface of a material. A small voltage is applied between the tip and the surface. Classically, no electricity should flow because there is a vacuum, a gap, between them. But because of quantum tunneling, electrons have a small probability of leaping across this forbidden gap, creating a tiny electrical current called a tunneling current. This current is extraordinarily sensitive to the distance. If the tip moves closer by the diameter of a single atom, the current can increase by a factor of 1,000. By scanning the tip across the surface and using a feedback loop to keep the tunneling current constant, the microscope can trace the contours of the material with unbelievable precision. The system records the up and down movements of the tip needed to maintain that steady current, and a computer translates this data into a three-dimensional image of the surface, atom by atom. For the first time, scientists were able to look at the fundamental building blocks of matter, to see how atoms arrange themselves to form crystals, and even to pick up and move individual atoms to spell out words or build tiny structures. Another piece of technology that relies completely on quantum tunneling is sitting in your computer, your phone, and your camera right now: flash memory. This is the solid-state storage that holds your photos, apps, and documents. Each bit of information in a flash memory chip is stored in a tiny component called a floating gate transistor. This transistor has a special floating gate that is electrically isolated, trapped inside a layer of non-conducting oxide. To write data, to store a 1 or a 0, we need to get electrons onto that gate or remove them. Tunneling provides the perfect mechanism to do just that, allowing us to build the dense, fast, and reliable memory that powers our digital world. For decades, the story of the electronics industry has been one of relentless miniaturization. Guided by Moore's law, which predicted that the number of transistors on a microchip would double approximately every 2 years, engineers have been making electronic components smaller and smaller. This has given us the powerful, compact devices we rely on today, from supercomputers to smartwatches. Each new generation of chip packs more power into a smaller space by shrinking the size of its fundamental building block, the transistor. A modern transistor acts like a tiny electronic switch, controlling the flow of electrons. But as these switches approach the atomic scale, quantum tunneling starts to turn from a useful tool into a major headache. A key part of a transistor is the gate oxide, a microscopically thin layer of insulating material that prevents electrons from leaking out when the switch is in the off position. To make transistors smaller and faster, engineers have had to make this insulating layer thinner and thinner. In modern chips, these layers can be just a few atoms thick, only about 1 nanometer. At this minuscule scale, the barrier that is supposed to stop the flow of electrons is no longer insurmountable. The electrons, behaving as quantum waves, can simply tunnel right through the supposedly non-conducting insulating layer, even when the transistor is switched off. This unwanted electron flow is known as quantum leakage current. It's a bit like having a faucet that drips constantly, even when you've turned it off as tightly as you can. This leakage creates a host of problems for chip designers. First, it wastes power. The electrons that tunnel through the gate consume energy without doing any useful work, which drains the battery of a laptop or smartphone much faster. Second, this wasted energy is converted into heat. As billions of transistors on a single chip all leak a tiny bit of current, the cumulative effect can be a significant amount of excess heat, which can damage the chip and requires more complex and expensive cooling systems. This leakage problem is now considered one of the fundamental physical limits to Moore's law. We are reaching a point where if we make the gate insulators any thinner, so many electrons will tunnel through that the transistors will no longer be able to function effectively as switches. They won't be able to hold a clear off state, making computation unreliable. Engineers are now fighting a battle against the very laws of quantum physics, developing new materials with better insulating properties, called high-K dielectrics, and redesigning the entire structure of transistors to mitigate the effects of tunneling and keep the era of miniaturization going for a little while longer. Even as quantum tunneling poses a fundamental challenge to the future of conventional electronics, Scientists and engineers are already finding clever new ways to turn this ghostly quantum effect back to our advantage. Instead of fighting against tunneling, they are designing new types of devices that embrace it and use it as their core operating principle. This shift in thinking could lead to a new generation of electronics that are not only smaller, but also dramatically more energy efficient than anything we have today. One of the most promising of these new technologies is the tunnel field effect transistor, or TFET. A conventional transistor works like a dam, where the gate voltage has to be high enough to lower the barrier and let a flood of electrons, the current, flow over the top. This process is inherently inefficient and requires a relatively high voltage to operate. A TFET, on the other hand, works more like a sluice gate in that dam. It is designed so that the gate voltage controls the thickness of a barrier, not its height. By applying a small voltage, the barrier becomes thin enough for electrons to tunnel through it. This allows the switch to be turned on and off with a much smaller change in voltage. The potential benefits of this approach are enormous. Because TFETs can operate at much lower voltages, perhaps as low as 0.2 volts compared to the 1 volt used in many current transistors, they could slash power consumption by a factor of 100 or even more. This would be a revolutionary breakthrough for everything from mobile devices, which could have vastly longer battery life, to massive data centers, which consume a huge amount of electricity and generate immense heat. Researchers are actively developing and testing TFET designs, hoping to overcome the manufacturing challenges and bring this ultra-low power technology into the mainstream. Beyond transistors, researchers are exploring tunneling for other advanced applications. It is a key ingredient in the development of quantum computing, where devices like Josephson junctions, which rely on the tunneling of paired electrons, are used to create qubits, the fundamental building blocks of quantum computers. Scientists are also investigating tunneling's role in new types of solar cells that could be more efficient at capturing energy, and in chemical sensors that could detect single molecules. By learning to precisely control and engineer tunneling, we are not just solving a problem, but opening up an entirely new toolbox for building the technologies of the future. Quantum tunneling is far more than just a strange paradox or a scientific curiosity. It is a profound demonstration of how fundamentally different the universe is at its smallest scales compared to the world we experience every day. It forces us to abandon our classical common-sense intuition and embrace a reality built on probability, waves, and uncertainty. The fact that a particle can pass through a barrier it shouldn't be able to cross shatters our simple mechanical view of the cosmos and replaces it with one that is far more subtle, interconnected, and in many ways more mysterious and wonderful. The importance of tunneling echoes through nearly every field of science. In cosmology and astrophysics, it explains how stars are born and how they generate the energy that makes life possible. In chemistry, it allows for reactions to occur in the freezing cold of interstellar space, seeding the cosmos with the building blocks of molecules. In biology, it offers a potential mechanism for genetic mutation, one of the core drivers of evolution. It shows us that the quantum world isn't a separate, isolated realm. Its effects ripple upwards, shaping the macroscopic world in countless ways, from the shining of the sun to the very code written in our cells. In our technological world, tunneling represents a classic double-edged sword. On one hand, it is the enabling principle behind powerful tools like the scanning tunneling microscope, which opened our eyes to the atomic world, and flash memory, which underpins our digital society. It is a force that we have learned to harness for incredible innovation. On the other hand, it stands as a formidable wall, a barrier of its own, that threatens to halt the decades-long progress of computer miniaturization. It is both a creative and a destructive force in our quest for technological advancement. Ultimately, the story of quantum tunneling is a perfect illustration of the scientific journey itself. It began as a strange prediction from a new and bewildering theory. It was then confirmed by observations of the natural world, solving long-standing puzzles. Finally, it was mastered and engineered to build revolutionary technologies, even as it presented new challenges to overcome. Tunneling teaches us that the universe doesn't always operate according to the rules we expect. By exploring these strange and counterintuitive phenomena, we not only gain a deeper understanding of reality, but also unlock new powers to shape our world in ways our ancestors could never have imagined.